Good morning. So we've got a little going on here with enthalpy, which, as you recall, that would be our old friend delta H. Pardon me while I'm looking around for stuff that I set down. Right there. Okay. So I don't know what I need to tell you. Can't remember other than in lab the kit for the enthalpy lab is on the back station. I think kind of by where Amber and Chloe do their labs. And then other than that, you should be good. God willing, and the creek don't rise. You needed to have your pre-lab done and checked off, and your homework done and checked off, which was that big giant, quote unquote, big giant Q heat homework package. And other than that, I think we're all right. This is kind of weird. I've heard kids say it's kind of weird not being able to see you while we hear you talk. Well, I don't know if it's quite as weird as sitting here looking at myself in this video thing. I'm not sure what I look like, but it is freaking frightening. Okay, so enthalpy, ready, fire, aim. There's a bunch of stuff on this introduction slide right here that is relatively significant. That's the one that is of any familiarity at the moment, that being delta H is the heat of reaction, and that little P right there means heat at constant pressure. And what that means is that enthalpy is the heat of reaction if the pressure is constant. Otherwise, it's that thing right there. Delta H is delta E plus P delta V, which is another deal. That P delta V is work. And we'll get into that a little bit a little later. We're just going to focus on enthalpy for a little while. Okay, ready, go. So some general info on enthalpy. Yikes, I'm not sure where to put that thing so it's not in the way. Absolute enthalpy is a little difficult to quantify, so what one sees is delta H, which the change in enthalpy can be quantified and can get your arms around it relatively easily, so that's what you see. Quantified as heat of reaction, mentioned that already. Constant pressure, in which case the energy transfer is the flow of heat. And the other method or methods of energy transfer other than the flow of heat, like I said, we'll get into that later. And there it is right there. It's a work function. All righty then. Everybody needs to see this. All AP chemistry students need to see this little deal right here on the formation of a chemical bond. I have seen this on an AP test. So what this little deal is right here is a potential energy diagram as a function of the distance between the nuclei. So can take this atom and let it go. This is a neon atom, and do something. It's supposed to move. Go. Do something. Fine then. So you can see there is as the nuclei or the atoms approach one another, the energy diminishes, and as the nuclei begin to get close to one another, the nuclei begin to repel and potential energy goes up. But right here, as the electrons, the valence electrons specifically, start to approach one another's atoms. The valence, oh, there it is. The valence electrons here begin to form an attraction with the nucleus there, and the valence electrons there begin to form an attraction with the nuclei there, and you get this little energy well right there. And in this case, it's no bueno. As you're no big surprise, neon's a noble gas, so it doesn't really form a bond. If we do the argon thing, about the same thing happens, although there's a little deeper energy well, and that's not surprising because argon's bigger than neon, and so the electron cloud is softer. But still, we don't get a whole big, wonderful grooviness. This is wonderful grooviness, quote unquote, right there. So these are oxygen atoms. And so as the oxygen atoms approach one another, look at that energy dip. Whoa. And I'm going to make it, there you can see it. So as the nuclei or the atoms approach one another, and the valence electrons are attracted to the nuclei in the bond. Whoa, I'm all funky looking in my picture down there. I don't know why. Nice. But this energy minimum right here is when the bond is formed. So this little picture right here, the potential energy diagram versus distance between atoms, when there's a significant little energy dip right there, that is when the bond is formed. And that is showing a lower energy of the atoms in the bond relative to the free atoms. So there's the free atoms right there. And the potential energy is what it is. And when the atoms come together and a bond is formed, and the atoms, this is kind of cool, it's showing the atoms vibrating. It's kind of showing me vibrating right over there. I don't know what that is. I don't like it. Nice. Anyway, it shows the formation of a bond. And I have seen this energy profile on AP questions. And check this out. So as the nucleus gets closer and closer and closer, the energy skyrockets high as the two nuclei get really close to one another, and the force of repulsion between the two positively charged nuclei gets great, and off the chart it goes. So anyway, there you go. One each bond formation as a function of distance between atoms, and groovy. All right. Am I going to fade in and out anymore? Maybe it was just that graphic that was making me all fuzzy. So that energy in the bond is called bond energy, and it is by definition the energy required to break a bond, or often referred to as the bond dissociation energy. And there's a picture of a bunch of bond dissociation energies. For example, the hydrogen-hydrogen bond is 436 kilojoules per mole, or in other words, it requires 436 kilojoules to break a mole of hydrogen-hydrogen bonds. And there you are, there's a whole bunch of them. There's the carbon-carbon bond is 347 kilojoules. The carbon-carbon double bond is 607 kilojoules, which is more than the carbon-carbon single bond, which would make sense for more reasons than one. But at the end of the day, there's more electron density between the two nuclei in a carbon-carbon double bond than in a carbon-carbon single bond, so it's harder to pull them apart. Back again, Coulomb's law is completely in control of all that. And over here, I can't have my, oh, there it is. The nitrogen-oxygen double bond, the nitrogen-nitrogen single bond, the nitrogen-nitrogen triple bond. And with all these double bonds and single bonds and all that stuff going around, I don't know if it leaps to mind, but it would be good if it leapt to mind that this is relatively Lewis structure E. It's a little difficult to get your arms around what bonds are being broken and what bonds are being formed without a structural formula around. Wink, wink, nudge, nudge. So, oh yeah. Man, I'm glad I put that on there because I'd completely forgotten about it. And I'm going to move that thing again. So, if the nitrogen-hydrogen bond, where is that thing? Right there. Is 393 kilojoules per mole. The bond dissociation energy is 393 kilojoules per mole. What do you suppose is the amount of energy released when 1 mole of nitrogen-hydrogen bonds are formed? Yeah, yeah, you're right. That would be 393 kilojoules. So it's strictly a function of the algebraic sign on the energy associated with the bond. One of them being broken, one of them being formed. And I think I've got that right over here. Oh, the two fundamental. Oh, wait. Pick up a pen. Ready, fire, aim. The two fundamental processes thermodynamically are bond forming. Yikes, this is hard to write with. And bond breaking. Oh, man. Bada boom, bada bing. And now we're going to go there. Come on, Butch. Let's see. Of these two processes, bond, I'll stick with that one, forming is an exothermic process. Back in that little graphic with the atoms forming the bond with potential energy versus bond distance, or distance between atoms, if you will, if there was not a lower potential energy when the bond was formed, the bond would not form. So bond forming is definitively an exothermic process, and that is, from that graphic, the difference in the potential energies of the free atoms versus the potential energies of the atoms in the bond. And if that were not an exothermic process, the bond would not form. Let's see. While on the other hand, bond breaking is an, I don't know if I can move that thing while I'm in writing mode, is an endothermic process. It requires energy to break a chemical bond, and I would hope that would be a relatively intuitive argument. You got to put energy into the system to pull two atoms that are bonded apart. You have to break the force of attraction between the electrons and the nuclei, regardless of the type of bond. Covalent, ionic, metallic, intermolecular, doesn't matter. You've got to put energy into the system to pull those atoms apart or break that force of attraction. All righty. And more specifically to the point of this discussion would be estimating delta H by evaluating the bonds that are broken and formed. And so it's a relatively common practice to estimate delta H of a reaction by looking at the number of bonds broken versus the number of bonds formed, and then summing those two processes. And since bond formation is an exotherm, it is negatively or the algebraic sign associated with that quantity is negative, versus an endothermic process where the algebraic sign is positive. If you take the endotherms and add the exotherms to them, the sum of that is either a positive or a negative value, which in turn determines whether the reaction is endothermic or exothermic. But the point being is one adds up all of the bonds broken and adds up all of the bonds formed, and then combines those two energies to determine the overall delta H of reaction. And that is done by enthalpy, bond enthalpy. Come on, Butch. For example, calculate the standard enthalpy. We'll get a little more into that quote-unquote standard enthalpy business here before we get a whole lot older. For that reaction right there in which propene reacts with hydrogen to form propane. And I've got room to write on the next page. And so there it is right there. So I'm going to, do I have a pen here? Pen. I'm going to draw Lewis structures, kind of a dumb Lewis structure, these guys. So there is a carbon right there with 3 hydrogens on it. Nice hydrogen base. Hooked to a carbon with 1 hydrogen on it, which is double bonded to a carbon with 2 hydrogens on it. And it's reacting with a hydrogen molecule, which is a hydrogen bonded to a hydrogen doi. And on the other side of the world, there are carbon, 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 and a bunch of hydrogens. Hydrogen, 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 hydrogen. Come on, man. Whew, alrighty then. So there's a couple of ways to approach this. The most common, if you look around, the most common that I have seen of late is to disassemble the whole pile on the reactants and assemble the whole pile on the products. And to do that, in the reactants, one would take carbon-hydrogen bonds, of which there is 1, 2, 3, 4, 5, 6 of them. 6 carbon, hydrogen single bonds. And I looked those up on that sheet of bond enthalpies, or that table of bond enthalpies that's a couple of slides up, but I can't get there from here. That was 413 kilojoules per mole. And there is 1 carbon-carbon single bond at a value of 347 kilojoules per mole. Wow. Nice. And 1 hydrogen-hydrogen single bond at a value of 436 kilojoules per mole. So what one does to get all of the energy required to break all those bonds is add them all up. So 6 times 413 is 2,478. 2,478 kilojoules. And one of those guys, man, that is horrible, 347 kilojoules. And that's 436 since there's only one of them, like that one. 436 kilojoules. And then add that pile up, and you get 3,868. 3,868. Wow. Kilojoules to break a mole of all of those bonds up there. And in this one, so these are broken. Wow. What is going on? Broken. Whatever. This is formed. Wow. Formed. Forget about it. Do you get that? That says formed right there. Oh my God. There are 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon, hydrogen. This is a wreck. Single bonds, whew, to the tune of 413 kilojoules apiece. And 1, 2 carbon-carbon single bonds. Yikes. To the tune of 347 kilojoules apiece. When you add all that up, yikes, you get 3,998 kilojoules. 3,998 kilojoules. And since bond formation is an exothermic process, that's a negative sign. And since bond breaking is an endothermic process, that's a positive sign, which looks more like a 4 than a positive. And then you just add those two quantities, and you have delta H reaction. And that turns out to be delta H equals negative 130 kilojoules per mole. And so taking the whole thing apart on the reactants and putting the whole thing back together as the products is the most commonly used method I see. It also works to just evaluate it on a case-by-case, bond-by-bond basis, in which case there is one carbon-carbon double bond broken and one hydrogen-hydrogen single bond broken. And I'm going to fool with this pen for just a second. Maybe. Come on. Pen color. Let's go with blue. And in this side of the coin over here, there is one carbon-carbon single bond formed and two carbon-hydrogen single bonds formed. So if you just evaluate it on that bond right there, that double bond right there being broken, and that single bond right there being broken, and that single bond right there, and those two single bonds right there being formed, it turns out to be the same thing. Go figure. And I did both calculations, and I was going to show you both, but this writing thing is not working. So take my word for it. And then I've got uno mas, which says something about, crap. Sweep down, get out of the way. Nitrogen reacts with hydrogen to produce ammonia. What is the change in enthalpy for the process using bond enthalpy data? This is a wonderful one because you've got to balance the equation and the whole enchilada all by your lonesome. Come on. Pen. So, nitrogen. Oh, groovy. Reacts with, oh, look at it go. Reacts with hydrogen to form ammonia. Sweet. Albeit that's not balanced, and there's 3 hydrogens there and 2 hydrogens there, and usually the way to go about that is just go like this, boink, boink, and then the number of hydrogens turns out to be the same, 6, 6, and 2 nitrogens and 2 nitrogens, and say hallelujah. So again, the whole Lewis structure idea is handy like fingers in a glove, in that the nitrogen is a triple bond, and there are three moles of hydrogen-hydrogen single bonds and 2 moles of nitrogen-hydrogen single bonds formed. So broken. Let me see, I'm going to mess around. Oop, easy pace. And color red. So in this deal, broken nitrogen-nitrogen triple bond and the hydrogen-hydrogen single bonds, and formed yellow, and formed, oh man, that's not groovy, you can't hardly see it. Oh, I can even draw a bond there. Way to go, Pace. Formed the 3 nitrogen-hydrogen single bonds, and then from there you head to the bond enthalpy data. And by the way, the bond enthalpy data, a couple of slides up there, is different than bond enthalpy data that you can find in books, and it's different from that found in Google. And the reason for that is not all nitrogen-hydrogen single bonds are created equal. Not all carbon-carbon single bonds and carbon-hydrogen single bonds are created equally. There's this whole argument of molecular orbital theory and the electron distribution throughout the molecule and inductive effects of electronegativity and electron densities in carbon-carbon single bond versus carbon-carbon single bond in another molecule, and those electron densities between those 2 carbon atoms in different molecules is different. Thus, with different electron densities between atoms, bond energies are different. So you pay your money, take your chances, and use the table you're given. And these are, in fact, estimates, but at the end of the day, they're not horribly bad. So, meanwhile, back at the ranch, broken, positive quantity. Oh, this is working so much better. 1 nitrogen-nitrogen triple bond, which is 941 kilojoules. Oops. Not surprisingly, a high value. And 3, since there are 3 moles in this reaction, 3 moles, wait, oh, yeah, we're groovy. We're groovy. Since there's only one bond right there, and 3 times that, there would be 3 times a nitrogen-hydrogen single bond, which is 436 kilojoules per mole each. And when you add all that up, you get 2,249 kilojoules per mole of bonds broken and then bonds formed, which is, of course, a negative quantity because bond formation is exothermic, and there are 1, 2, 3 nitrogen-hydrogen single bonds and 2 moles of them, so there are 6, at the end of the day, 6 moles of nitrogen-hydrogen single bonds formed at the tune of 393 kilojoules a copy. And when you add all that up, that would be 2,358 kilojoules. And since that is a negative quantity, that's a negative quantity, and delta H is, add those 2 quantities, so delta H of that reaction right there is, when you add those 2 quantities, I believe you get negative 109 kilojoules, starting to lose it, per mole. It's the amount of graphics on the page that is apparently freaking everything out. And there you go. Delta H by bond enthalpy or bond dissociation energy. And that's it. So again, in summary, what one does is determine the number of bonds broken, the total number of bonds formed, attach the appropriate algebraic sign to the formation and the breaking of the bonds, and add the quantities, and voila, 1 each, delta H of reaction in kilojoules per mole. And please note, I don't know if I can write this. I'd like to write this, and I'm going to try. Pen color. I'm going to go back to blue to make it look like that. There is a semicolon and a delta H. Oops. Oh, I can't go back. Usually there is the quantity of heat right there, only it doesn't say delta H. And it says negative, 109 kilojoules per mole. That per mole right there means per mole of reaction, not 1 mole of ammonia, 2 moles of ammonia. Not 1 mole of hydrogen, 3 moles of hydrogen. And yes, 1 mole of nitrogen, because it's the stoichiometric coefficient right there is 1. And you can use that value in stoichiometry if one is doing a stoichiometric calculation. This becomes a part of the balanced, quote, an important part of the balanced chemical equation, where 1 mole of nitrogen reacts with 3 moles of hydrogen and produces 2 moles of ammonia. And the heat involved with that process is negative 109 kilojoules. And so that per mole thing right there sometimes gets students wrapped around the axle because they're going, oh my God, is that 1 mole right there and 1 mole right there? No, it's with the reaction as it's written. If it were 1 mole of ammonia, then the 1 mole of ammonia would limit the reaction, and the amount of heat produced could not be that much. It'd have to be cut in half. And 1 mole of hydrogen would cut that amount of heat in thirds because you'd run out of hydrogen. way too soon. Okay then, I believe that's it. Take care then, bye-bye now. We will see you mañana.